All right, we're back recording. Last few minutes of class, I want to set up the next topic. So tomorrow I want to do an activity with this, and then um, I want to plant some ideas that when you guys come back from Thanksgiving break, you will have seen some of the stuff, and it's going to be that much easier to pick up. So here's our next topic: is going to be momentum. Momentum is very simply mass times velocity. It's a vector quantity, which means that directions matter again. Like last few weeks, we will work with scalars, but now we're back to vectors. So if something's going to the right or to the left, it's going to matter. This is a property that's conserved and it's especially used for solving collisions. I want to sort of kickstart this with an example, or at least get you guys thinking about this. And then by the end of class, show you guys how to solve this using this momentum principle. Right. So let's go Magic School Bus. So they go inside this textbook that they have a zero friction baseball field. You guys see all those kids sliding around right there? Who's ever been ice skating? You guys been ice skating? Yeah, that's a very low friction environment, probably pretty similar to this, right? Right. And when you're out there first, it's hard to maintain your balance, right? Once you're sliding, it's kind of hard to speed up, slow down, or change direction, right? Because you have so much inertia, but hardly any force to work with, right? So all these kids have to be put. Oh, look, they're having trouble maintaining balance. Did they already break out the crane? They'll put them. Oh, see that little crane? Put them around. Get on second base. Oh, it's not second base. Whatever. Right? So because once you're sliding with no friction, there's no way to just walk. Oh, I'm gonna just walk out to shortstop and just no, because there's no ground to like push against no friction. And once you get out there, there's no way to stop. So you have to be put in place. There's no trouble maintaining balance. Yeah, so yeah, just think about like what a zero friction surface would look like. Right? You might get might break out some low friction carts system here pretty soon. Right? So all right, it's right at the end of this clip. All right, there's all right, what us to be thinking about. All right, batter up, throw that baseball. I wonder what's gonna happen. Or wait, maybe I should have you guys guess. If she throws the baseball forward and there's zero friction on that surface, what's she gonna do? Go back towards second base? Let's see. Oh, man, I think you guys are good at physics. Let's see. Whoa, oh, she did go back towards second base. How did you know? What law of motion is that? Equal and opposite forces. That's right. That's kind of like Newton's third law, isn't it? Right? While she was throwing the ball, there was a force she was putting on the ball. Was the ball putting a force back on her? Yeah, but which force was bigger? The same force. Same force. Wait a minute. Which object do you think is moving faster? The ball forward or her backward? Who thinks the ball is moving forward faster than she's moving backward? Yeah. I think the ball's moving faster. Right? How? Because the ball has less what? Less mass. Yeah, less mass. Right. So while she was throwing it, maybe the ball was it had greater acceleration. Okay, I'm just do a little recap from the past. Okay, so you guys got that? All right. Now that force only acted for a tiny fraction of a second. Right. Here's kind of the question I'm trying to get towards: is if you know the mass of the baseball, the speed of the baseball, and her mass, can you calculate how fast she's sliding back towards second base? Right? You guys get that? You know, the mass of baseball, the speed of the baseball, and her mass, how fast is she going back towards second base? Right? Now, you could sort of solve it with the physics you know already, but you have to go through acceleration. So you have to say, well, if I know the final speed of the ball, and I know, say, either the time or the distance interval she was throwing it, I could calculate that acceleration, multiply by the mass of the ball, get the force, Newton's third law, send equal and opposite force on her, divide by her mass, get the acceleration while she's throwing it, which is time fraction of a second. Go back to kinematic, how fast you go back. Woo! That's a lot of paper and a lot of time. And also you have to kind of guess how much time she was throwing the ball for, which is kind of crazy, right? But there's a much simpler way. You cut through all that. You just cut straight through it. And that's what this momentum conservation principle that we're going to be doing. All right. So, okay, you guys get kind of the premise where we're going with this? All right. At least that's one fun example of this. So let me go through some momentum slides, and then we're going to look at these posters. And then at the end of class, I'll show you guys how to solve that question. All right, so we got this property in physics called momentum. I'm going to use this letter P. Guys, what does that little arrow mean above the, what's that little arrow? It means it's what kind of quantity? Vector, right? Which a lot of times I leave off the arrows, but you could have them there, right? I'm really trying to emphasize that direction matters. If someone's going right or left, up or down, backward, forward or backward. Right. Okay, so you guys that. And I'm saying this is usually applied to collision physics. Hey, if I ran that video you guys just watched, Magic School Bus, in reverse, would it look like a collision? Like she's sliding towards the mound and the baseball, and they collide and just land on the mound together? Right. So that is a collision in reverse, sort of. Right. All right, let's take a look. So just to remind you guys, closed system, open system, here's a different perspective. So if it's a closed system, the old way of thinking was, well, there's no energy entering or leaving, or maybe there's no external force. Now, here's the same idea, just different context. Momentum is conserved. Sum of momentum before the collision equals sum of momentum after the collision. Right, you guys got that? If it's open, maybe there's an external force for some time interval. We'll talk about that later, called an impulse. We'll stick to closed for just last few minutes here today. Right. So here's a really generic example. I got two balls headed toward each other for just one dimension. Right? They collide, and then maybe they rebound off each other. Right. Now, if you do mass times velocity here and mass velocity here, and you add it all up, that's the pre-collision momentum. Right. It's the sum of momentum pre-collision. MV there. That's this and this. Right, you guys got that? Right. Now, see if you guys are following. If this is going to the right, this is going to the left. Do these momentum sort of subtract from each other because opposite direction, right? So I bet this could be a positive value and this could be a negative value, right? In fact, it might possibly be zero momentum in the system, maybe, if they're going against each other, possibly, or maybe there's some momentum left, right? Anyway, regardless, after the collision, if you do this MV and this MV, this one's going backwards, might be a negative value. Watch that, right? It has to equate. The momentum before and the momentum after is conserved, right? You guys got that? Right? And we can use that to solve all kind of puzzles, right? Now, the next question is, well, what type of collision are we talking about? Because these could bounce off each other really well. Like, actually, here's a really good example right here. This is called elastic, where it's like perfectly bouncy, or as close as I can get. The other extreme is you could have two balls of wet clay going and just stick together, and they don't even rebound because they stick, right? Regardless, or it could be anything in the middle. It could be two half-deflated tennis balls, like, regardless of which of those scenarios it is, this statement is always true in this gold box right here. Right? So let me show you guys real fast. Here's perfectly inelastic, like two balls of clay that stick together. Look at that. It starts out the same. Got mass velocity bits. I'm adding them up. Hey, look, they make one giant mass, moving a common final velocity. You guys going to see that in the future? Right? Now, perfectly elastic, the math is a little trickier. Momentum's conserved. So is, you guys remember kinetic energy we've been talking about? It turns out only for this type of collision, only for perfectly elastic, kinetic energy also happens to be conserved. System of equations can solve that. So just look for that in the future. You're not time today. Right. But here's what I do. And last, great, we got perfect amount of time. Right, let's solve that magic school bus question here real fast. Right, so here's your picture, baseball. Now I just made up some crazy numbers, but let's say got a ball of 1 kilogram, which is too heavy, but whatever, right? And let's say the mass of the pitcher is like 50 kilograms, right? And let's say the ball gets thrown, let's call it 10 meters per second. Now I do have to apply a direction. You guys see I'm calling it negative. Maybe negative could be left and positive could be right. There's enough info here I could solve for how fast is she sliding back towards second base. You guys get that? Right? Now, when she was standing with the baseball in her hand on the mound at rest, how much momentum was that equal to? Zero, right? In fact, there's only ever zero momentum in that system. I mean, I thought the ball had momentum going to the left. Yes, it does, but she has momentum going to the right, and it cancels out. It always zeroes out. The fact that I know that, I can say equals, and then here's mass of the ball times velocity of the ball. Notice I'm calling it negative. It's velocity. Whoops, I should have meant to do plus here. Plus, this is plus. Mass times velocity going to the right. Then you can solve for this v. Just do a little algebra. And well, if I plug in these numbers, this is how fast she's headed back towards second base. That's it. Notice what we cut through. We never solved for any accelerations. We never solved for the force while she was throwing the ball. We never had to know the time interval she was throwing for. No, none of that. We just cut straight through that and solved it in like 3 lines. Get that? All right. All right, so that's something to look forward to. All right, that's going to be a wrap on class today. Guys, make sure that quarter page is in the grade tray, and we'll continue this adventure a little bit tomorrow.